In this video, we're going to look at some example problems where we use stoichiometry and our mole conversions to solve problems in chemistry. The first thing we're going to do is we're just going to refresh our memory. So if we have a mole, we can go from moles to mass using the molecular weight, which is in grams per mole. And we can go from moles to the number of things using Avogadro's number. Now, what we learned in the last video is that if we want to go from moles of A to moles of B, or any one reactant or product, we use the ratio of A to B in the balanced reaction. And then from there, we can get to the number of things or to the mass using the molecular weight of B. So this is the molecular weight of B, or Avogadro's number. So I wanted to have that up there. This is going to kind of help us to set things up as we go along. So we're going to do problems 1 and 3. 1 is very simple, and it's just sort of a demonstration of the mole-to-mole ratio. And then we're going to do problem 3, which is more consistent with what you would see on an exam, for example. And that's going to be a mass-to-mass type of problem. Okay, so for the first one, it says how many moles of SO2 could be produced from 0.34 moles of O2. So we start with 0.34 moles of O2. And the reason why I'm doing this problem is because this is going to allow us just to reintroduce the mole-to-mole ratio. So if we wanted to write a unit conversion for O2 to SO2, we know that for every 3 moles of O2, that is going to give 2 moles of SO2 as a product. So in this case, what we could do is we could say, well, for every 3 moles of O2, we would produce 2 moles of SO2. So when you multiply the 0.34 times 2 and then divide by 3, you're going to get 0.23 moles of the SO2. So that's a demonstration of how to do the mole-to-mole ratio, where we are going from moles of A to moles of B. Now let's look at one that's a little bit more challenging. So here we go. So we have a reaction produces 25.34 grams of zinc oxide. How many grams of O2 were used in the reaction? So in this case, we're going from zinc oxide to O2, and so our ratio is that for every 2 moles of zinc oxide, we had 3 moles of O2. Okay, but the problem is we're starting with grams. So in this case, we have to go from grams to moles in order to get closer to going from moles of zinc oxide to the moles of the O2. So to do that, we have to use the molecular mass. So we have 25.34 grams. And we give you the molecular weight in this problem of 81.38 grams for every 1 mole of zinc oxide. And you'll notice that to be a little bit careful, you should always write what you have. So see how I write 25.34 grams of zinc oxide, 1 mole of zinc oxide, and 81.38 grams of zinc oxide. That's going to help you keep track, because when you do your mole-to-mole conversions, you have to make sure you know not only the number of moles, but the moles of what. So grams are going to cancel, and we're good. So now we're in moles of zinc oxide. So now we can do the next phase. So if we look at our chart up there, we can go from moles of A to moles of B. So in this case, we're going from moles of zinc oxide, so 2 moles of zinc oxide, to 3 moles of O2. All right, so that's good. So now we've gone from moles of A to moles of B. And then the problem says, well, how many grams of O2 were used in the reaction? Well, we can do that. We can go from moles of B to mass using the molecular weight. For every 1 mole of O2, there is 32 grams per mole. And we get that from the periodic table. And this is going to give us a final answer. So if we multiply 25.34 times 3 in our calculator, and then we multiply again by 3,2, and then we hit the divide button by 81.38, and then we hit the divide button again by 2 moles, we get 14.94 grams of O2. So you can see this takes us across and uses the full mole-to-mole calculation. Okay, so let's look at lecture question 1, and this is going to be another example of how we can use stoichiometry. So it says in the past, chlorine was generated from hydrochloric acid by treating it with the mineral pyrolusite, which is MnO2, according to the reaction above. Calculate the mass of MnO2 in grams that would be needed in order to completely consume 0.24 grams of hydrochloric acid. Okay, so this is going to be another mass-to-mass conversion. We have a mass of one reactant. It's asking us for the mass in grams of another reactant. So we're going to take our 0.024 grams of the HCl. We have its molecular weight, which is 36.46 grams for every 1 mole of HCl. And now we have to look up our conversion factor from HCl to the MnO2. So it's a 4-to-1 ratio. So every 4 moles of HCl, we have 1 mole of MnO2. And in this case, for every 1 mole of MnO2, we have 86.94 grams. We give that to you in the problem. And so when you multiply 0.024 times 86.94, and then you press the divide button, divide by 36.46, divide by 4, you get a value of 0.0143 grams of the MnO2. Now here's where things start to get a little interesting. There are a couple of additions to this process. We can start to throw at you some new things, or at least what we can start to do is we can start to combine some concepts from Chapter 2 and Chapter 3. One way that we could do that is, for example, this next problem is going to ask us about percent composition. So we're going to throw a percent composition in, and you're going to do stoichiometry to have to figure out that percent composition. Now, other things that we could do is we could throw density into here. You can kind of think of this as when you're doing the moles, you can get to a mass, right? And we can use grams per mole, but we could also do it. We could also throw a density in there. So density is grams per mil, which would allow you to go to a volume. So don't forget that. I'm just throwing this out there because there's going to be some homework problems. There could be a problem on the test that might involve a density. Don't forget that you have that unit conversion in your pocket as well. I don't necessarily put it into the big chart because I don't want to make it too confusing, but we have that in our toolkit from Chapter 1. So don't forget about that also. But let's look at this last one because this is a really good problem. This one says a sample containing MnO2 and other impurities with a total mass of 2.54 grams is reacted with excess HCl, yielding 1.27 grams of MnCl2. Calculate the percent composition in the impure mixture. So let's start to break this problem down a little bit. What this problem is saying is, okay, you got a sample, and that sample is going to contain MnO2 and some other stuff. And the whole thing is 2.54 grams. So if we want to do a percent composition, we have the mass of whatever we're interested in divided by the total mass times 100. So the whole thing weighs 2.54 grams. So we're going to throw that in on the bottom. And we want to know what percentage of this thing is MnO2. So what we need up top is the mass of MnO2 out of that total mass of 2.54 grams. So it says a sample, which weighs 2.54 grams, is reacted with excess HCl. So we figure out how much MnO2 is in it from this amount of products that we make. So it yields 1.27 grams of MnCl2. So now what we have to do is we have to work back and we have to get from the MnCl2, well, how much MnO2 reacted from that value, the value of MnCl2, the manganese chloride, how much MnO2 would have reacted to give us that amount of MnCl2. And then once we have that, we can put that into our percent composition calculation. So if we had 1.27 grams of the MnCl2 at the very end, the question is, how much MnO2 would have reacted to give us that amount of MnCl2? We can take the molecular weight of the MnCl2, which is 125.84. We don't give that to you. Grams, so you have to figure that out. For every 1 mole of MnCl2. And then we can work back. And now we have to look up what the mole ratio is for MnCl2 to MnO2. And it turns out that it's a 1-to-1 ratio. For every 1 mole of MnCl2, there is 1 mole of MnO2. And then if we want to get the mass, we use the molecular weight. For every 1 mole of MnO2, there is 86.94 grams. So when you do the multiplication, this gives you 0.877 0.4 grams of the MnO2. And we can now plug that into our percent composition calculation. So we'll do that now. So if we take 0.8774 divided by 2.54 and we multiply by 100, we get 34.5% as our final answer. So that's our final answer. Now there's one thing that I want to point out in this question, because it's a good thing that's going to introduce us to the next concept. So when you run this reaction, it says the sample containing the MnO2. So just to kind of recap, what you have is you have MnO2 plus you have other stuff. The other stuff isn't doing anything. And they react this with the HCl, and it's going to give you your MnCl2. So now, in order to figure out how much MnO2 was in that, you have to take the MnCl2 that you got out, go back, and figure out, well, how much of the MnO2 is there. Now, there's one thing that I like to point out. There's this word excess here, and this is really important. Now, in order to make sure that we react all the MnO2, we have to have enough HCl to get all of our MnO2 to go to products. So it's important that we have what's called an excess of the HCl. And we talked about this in the first video when we were talking about the sandwich. If we want to, if our product is, if we want to make sure that all of the MnO2 goes to product, all of the other reactants must be in excess in order for that to happen. Because if they're not, if another one of the reactants is limiting, then we're not going to use up the thing that we want to use up. So that's why we write excess there, and I just want to make that point.